Howdy everyone, my name is Saishab and today I'm here with Nefemi, Tanvi and Kranti, and we will be presenting our project on implementation and analysis of path confidence-based Lookahead prefetching. The overall presentation is divided into 4 parts where we will start with an introduction to signature path prefetcher, and then we will talk about its architecture and how we implemented and evaluated our SPP, and finally talk about our simulation results and our analysis. Now, even though the processing speed has been increasing rapidly, the memory speed has not quite been able to catch up with this, thus limiting the overall performance of execution, also known as the memory wall problem. To tackle this issue, we use very fast memory like cache, which sits between the processor and the main memory. Different architecture employs different levels of caches, such as level 1, level 2, last level caches. Now we know that cache misses are really expensive, and that's why we need something that can make the data available to the cache even before the execution requirement. For this reason, we use prefetchers to better hide the memory latency and thus increase the performance. The cache prefetcher monitors the access request that is sent to the cache by the processor, and based on these access patterns, it tries to predict what would be the potential next accesses. And then it issues the prefetch request and brings the data into the cache even before the access is required. So we have understood why prefetching is an essential part of improving performance, but what should be our expectation from an ideal prefetcher? An ideal prefetcher should have a better coverage, which is the fraction of baseline cache misses that is pulled to the cache prior to their reference. For instance, if there are like 10 cache misses without the use of the prefetcher, and with the use of prefetcher 9 of the misses become fetched, then we can say that the prefetcher has 90% coverage. It should also have a good accuracy, which is the number of cache lines being used that were pulled to the prefetcher. For example, if 100 lines are being fetched, but out of those 100, only 70 are being used, then we can say the accuracy is 70%. An ideal prefetcher should also be able to identify complex memory access patterns, and based on that, predict the next access and classify them as useful or useless. Some of the early works done by A.J. Smith or T-Chan and others shows us how we can perform prefetching for sequential or stride-based access patterns. However, when the access doesn't follow such a sequential manner, we need some sort of prefetching technique that can detect complex access pattern. Therefore, the inspiration for our project is taken from the work done by J. Kim and others in their paper, Path Confidence-Based Lookahead Prefetching. In their work, they have implemented the SPP on the ChamSim simulator. For our project, we have done our implementation of SPP and observed the overall performance when we change different parameters, which we will cover in the later slides. Now, we may want to ask, what is SPP and why are we interested in it? SPP, or the signature path prefetcher, is a sophisticated prefetching technique that works on the principle of confidence-based lookahead prefetching. SPP maintains a signature for each access pattern in a compressed form, and unlike a sequence of stride-based prefetcher, SPP is able to look beyond the page boundary, thus producing better prefetching. One of the important aspects of SPP is its confidence value, and the way it works is that the SPP keeps prefetching until confidence value falls below a certain threshold. Also, the study shows that SPP achieves an average 27.2% performance improvement compared to the baseline without prefetching, and outperforms non-lookahead prefetchers by 6.4% on average. Now that we know how SPP is beneficial, let's talk briefly about the design overview. The SPP module is composed of 4 primary components, namely the signature table, pattern table, prefetch filter, and a small global history register. The elements work together for enhancing cross-page boundary learning. The signature table monitors the 256 most recently accessed pages and captures their access pattern histories as compressed 12-bit signatures. The pattern table uses these signatures to index and retrieve predicted delta patterns, accessing the likelihood that these patterns will result in beneficial prefetches. If the pattern has high confidence, it is sent to the prefetcher candidate to the prefetch filter, when the, uh, which then eliminates any redundant prefetch request. Should a prefetcher request cross a 4 kilobyte physical page boundary, the SPP avoids issuing the prefetch and instead routes this information to the GHR to facilitate learning about page boundary behavior. The SPP's effectiveness stems from its ability to learn from L2 cache access and to direct prefetch request to either L2 or LLC based on the confidence level, the prefetch prediction.
An example of how SPP works. So say we have an access to page 3 with an offset of 3. The first thing we're going to do is find the tag of page 3 in the signature table. And then we're going to update the latest offset from the previous value of 1 to the new value of 3. And then we're going to calculate the new signature and update that as well. The new signature is given by taking the old signature, left shifting it by 3 bits, and taking the XOR with the delta. The delta is simply this new offset minus the previous offset. So in this case, 3 minus 1 is 2. So we take our signature of OX1, left shifted by 3, and XOR it with 2 to get a new signature of OXA. We also update the pattern table. So in this case, our index is OX1, which is the signature, and our offset was plus 2. So we update the signature, the C delta from 7 to 8, and the C signature from 9 to 10. We're going to look at how to look ahead. So say we have a signature OXA. We look in the pattern table for an index that matches this signature. And then we calculate the path confidence value, which is simply given by C delta divided by C signature for the case where lookahead depth is 0. So in this case, we take 8 divided by 10 to get 0.8. And then we check to see if this path confidence is greater than the prefetch threshold. If it's greater than the prefetch threshold, then we prefetch, else we don't prefetch. And we also check if it's greater than the fill threshold. If it's greater than the fill threshold, then we place in the L2 cache, else we place in the LLC. In this case, since we are assuming that it is greater than the prefetch threshold, then we go ahead and calculate the new signature, which is simply given by OXA, the old signature, left shifted by 3, and XORed with the delta of 2 to get OX52. Now let's look at a situation where the lookahead depth is greater than 0. So we take the same signature that we just calculated, OX52, and look for the same index in the pattern table. And we calculate the path confidence, but this time the formula is a little different. It is given by path confidence equals alpha, which is the global accuracy scaling factor, multiplied by C delta divided by C signature, multiplied by the previous path confidence. So in this case, our global accuracy scaling factor, 0.9, multiplied by 5 divided by 8, multiplied by previous path confidence of 0.8. And then we check to see if this value is greater than the prefetch threshold, and if it is, we prefetch, and if it's not, we don't. And then we also check the fill threshold value. And then we calculate the lookahead prefetch for the next one. We keep going until the path confidence falls below the prefetch threshold. Global history registers help resolve a challenge many other prefetchers struggle with, which is a loss of information across new physical pages. In this example, when offset 62 tries to prefetch, it runs into the page boundary. A conventional streaming prefetcher must stop prefetching because it's impossible to predict the next physical page number. However, the boundary crossing prediction can still be useful when the next page is accessed for the first time. In order to track this, we store the prediction in the global history register. We store the signature, the path confidence, the last offset, as well as the delta. So in this case, 62 tries to prefetch 3 and runs into the page boundary. So we're going to store the signature, which is OX52, the path confidence 0.45, the last offset 62, and the delta plus 3. If we access a new page that is not currently tracked, the SPP will search the global history register for an entry whose last offset and delta matches the current offset value in the new page. So in this case, on the first access to page B, we're going to search the global history register. We find that 62 plus 3 equals 65, and 65 minus 4 equals an offset of 1. So we have an offset match. So we're able to keep prefetching. So again, we calculate the new signature value, OX52 left with the 3, XORed with plus 3 to get OX293.
We are now going to discuss about our implementation in ChamSim simulator. So ChamSim is an open source cache simulator maintained by Texas A&M and with the support of computer architecture community. It is used for performance analysis of different microarchitectures by measuring the number of instructions, cycles, IPC, cache hit or miss rates, branch prediction accuracy. It is capable of simulating different replacement policies, prefetch techniques, and cache memory models. Originally, it was developed as a simulator for championships. That's why it's called ChamSim. We have used the following configurations for our implementation, where we have L1 data cache of 48 KB, L2 data cache of 512 KB, L3 cache of 2 MB, and we have used bimodal branch predictor with LRU replacement policy. We have implemented the SPP as L2 cache prefetcher using the following classes, like signature table, where we have maintained information related to signatures of different access pages, their validity bits and tag bits, and we have also recorded the LRU related data. And in pattern table class, we had the information of delta and corresponding confidence values of sets and ways. In prefetch filter, we have stored the prefetched address and checked if this prefetch is needed or not. And in global register, we have stored the history of previously prefetched events, their confidence values and offsets and delta values. Later, we have completed the implementation of predefined functions of prefetch initialize, cache operate, and cache fill. In initialize, we have initialized the different SPP configurations, and in cache operate, we have updated various tables whenever there is memory access, and in cache fill, we have checked whether the evicted address needs to be added to the prefetch filter or not. For evaluation, we have compared the existing baseline SPP with our current implementation at by varying different configurations. So for this, we have considered the following performance metrics, where speed up is defined as IPC of new to the original implementation, where higher speed up indicates the effectiveness of the prefetcher, and coverage is a measure of number of useful prefetchers with the number of misses without the prefetcher. It basically explains about the hit rate. So the number of misses that are being effectively eliminated is indicated by this parameter. Then the accuracy is the ratio of useful prefetchers to the sum of useful and useless prefetchers. It measures how many unnecessary prefetchers have been taken, and it talks about the position of the cache. Later, for evaluating, we have considered PF threshold and fill threshold as our parameters, where PF threshold determines whether the specific prefetch is to be considered or not, and fill threshold determines whether the prefetch data needs to be placed in L2 cache or LLC cache. So we have varied this PF threshold from 15 to 50 and fill threshold from 45 to 90. So we have used these following 8 benchmarks for analyzing our performance.
We are analyzing the simulation results we have achieved through our implementation, and here the first graph shows us the speed up compared by varying SPP parameters to the existing SPP implementation as a baseline. We have done it for these 8 benchmarks, and we have varied PF threshold and fill threshold values. I mean, the PF threshold values are ranging from over 15 to 50, and then fill threshold values ranging from 45 to 75. We are varying these two parameters because they regulate the prefetching behaviors based on the confidence levels. That's how varying PF threshold and fill threshold can affect our accuracy, coverage, and speed up. Here, PF threshold is a threshold value which determines whether a prefetch candidate with a confidence level above it should proceed with the prefetch operations or not. The speed up here is with respect to existing SPP implementation. As we can see, there is a negligible variation in speed up, but it is definitely not getting any better with the increasing threshold value. And the accuracy is increasing with increasing PF threshold value. This is because increasing PF threshold value makes the prefetcher more conservative. It reduces unnecessary prefetches and potential cache pollution at the cost of missing some prefetch opportunities. This is the reason why we can observe here that the coverage is also not changed significantly. Depth accuracy and coverage are varying with increasing fill threshold values. There isn't a significant change, or we can say the change in speedup is almost negligible. We observe accuracy is increasing. Increasing the fill threshold reduces cache pollution by prefetching only high confident candidates, potentially improving hit rates for genuinely useful data and overall cache cleanliness. Similarly, we can observe a greater coverage for L2 cache SPP with a lower fill threshold value. As the fill threshold value decreases, the confidence with which the data can be placed in the L2 cache decreases. If the prefetcher confidence exceeds the fill threshold value, the prefetched value will be directed to the L2 cache. Otherwise, else it will be directed to the LLC. This dynamic explains why coverage varies significantly with different fill threshold values. So after analyzing various confidence parameters, we developed our signature path prefetcher as an L2 cache prefetcher and conducted a comparison with an existing SPP implementation. The speedups achieved by both implementations using no prefetcher as the baseline are nearly identical. Our implementation neither improves nor degrades when compared to the existing SPP implementation.
In conclusion, we can see our SPP implementation is almost similar to the baseline implementation, with the exception of few where we could see a slight improvement in the speedup. We have also seen that the changing some of the parameters such as fill threshold and PF threshold can improve the accuracy quite a bit and show us a slight change in the speedup too. The baseline SPP itself performs very well, and our implementation was able to match the expected performance for almost all the benchmarks. In the worst case, we saw the SPP matches the IPC, and in the best case, we see that SPP has a speed up of up to 1.6 times. For future work, we believe along with SPP, if we can use a simpler prefetch with a hybrid selection mechanism, this will save hardware resources when the memory access pattern is simple. Further, integration of AI enables prefetching to dynamically adapt recognized patterns and optimize prediction for improved efficiency and performance. We hope you liked our presentation. Thank you.